Hi everyone, my name is Hui Wen. I'm a PhD candidate from the University of Electronic Science and Technology of China. My work is about communication efficient federated data augmentation on non-IID data. This presentation has 5 parts. The first part is the background. Federated learning as a distributed system, she faced the challenges of the non-IID data due to the different local environments and the characters of the device. And at the same time, the limited link resources in wireless communication is another bottleneck. So to deal with these problems, we designed a federated data augmentation, FEDA, to deal with the non-IID challenge with the communication efficiency. The purpose of the FEDA is to create an IID foundation in each devices with the cooperation of the center server. And to achieve the data augmentation, the generative model is leveraged. The key characters are concerned with the communication between the devices and the server, and we should protect the data privacy. As we can see from the figure 1, the local non-IID data is fixed as IID data because of the existence of the generator. And conditional autoencoder is chosen as a generator. In the components of the CVPR, there is an encoder and the decoder. The original samples as the input of the encoder, and the lightened variables as the output of the encoder and the input of the decoder. Condition contents of the label information from the original sample is acts as the input of the decoder as well. And the decoder of the output of the decoder is labeled and generated samples. And these samples can be used to recorrect our non-IID dataset to IID dataset. So the CVE is trained. The main work is about the CVE, how to train in federated learning. So, the CVE is trained by the local data and constrained by 2 parts. One is the data reconstruction process is regularized, and the sampling process for lightened variables is constrained. In the reconstruction process, the CVE is regularized as a federated sightings to leverage all the sample information from all the devices. And to achieve the distributed learning in federated sightings, the knowledge distributed mechanism is utilized, and for the communication efficiency. The knowledge distillation mechanism helps one neural networks to learn some useful information through the knowledge from other neural networks. So in FEDA, the mechanism minimizes the difference between the local information from the devices and the global information from the server. And the difference is measured by KL divergency. And the local knowledge is designed based on the per label hidden layer features, and from the fully connected layer before the deconvolution layer. And as we can see from the figure 3, the knowledge is from this layer. So at the same time, we use the attention score to optimize the knowledge. The attention score is a measurement from the attention mechanism, and the attention score is applied to signify which information the decoder is most concerned with. And the hardware products are utilized to extract the significance and the general information in each class. The knowledge is shared between the devices and the server. The local knowledge is designed based on the attention score, and the global knowledge is calculated by averaging the local knowledge from the participating devices. And then the knowledge consumes fewer communication resources compared with the model weights or gradients. So that's we use this way to achieve efficient communication. And the loss function of the data generation is as shown in Formula 4. And we can see from the figure 4, there is a loss function of the knowledge distillation and the loss function of the CVAE. And the two loss function is balanced by the parameters lambda. And this is the local training part. And we can see there's a server. Server average the local knowledge that and download by that knowledge download by the each server. We train our CVE by reconstruction. Meanwhile, we use a sampling process to constrain the training process. And the CVE is constrained to generate cross-class samples. And we hope that samples can be distinguished easily. So the mean value of the licensed variables for each class is assigned a unique value to distinguish the peaks of the Gaussian curve from the different classes. And the mean value of the same class is set to be the same across devices. And the mean value satisfies the 3 sigma rule. This is the main procedure of the FEDA. And then we do some simulations. Like we use fashion MNIST and CVPR as our data set, and we build use our own rule to build non-IID data set. There is some baselines as competitors, and we can max the FEDA with a standalone and some other ways. And in our experiments, we trained a classifier. That classifier to utilize to classify our generated samples. So we record the average accuracy of the classifiers. As can be shown in in both table, the FEDA with a standalone and FEDA with a FED-AVG is the accuracy is higher than the standalone and a FED-AVG, and that's shown our FEDA improved the accuracy a lot and do a very good job. And at the same time, we record the communication in each communication round to show how to reduce the communication, how to achieve communication efficiency. And we record the total bits of the training process. And it's very easy to see we reduce a lot of the communication bits. And we visualize the generated samples, and we record the reality score to measure the quantity of our generated samples. And at last, we analyze the effectiveness. We do application experiments, and we analyze the effectiveness of the sampling process for the latent variables and the function of the attention score. That shows that experiments tell us it works very well. And then thank you. If you have any questions, please let me know. Yeah. Thank you for listening, and thank you for your time.